Okay, there. Officially, class has started. Happy Garbage Day. Happy Halloween Hangover Day. I have to tell you, Saturday morning, my son is in a bowling league, so we were driving around downtown, and you're familiar with the expression, the walk of shame? College students. The Halloween morning after walk of shame is especially fun to observe. I saw a college student, like a dude who's like 6 foot tall in a bunny costume, just walking down the street at 10 o'clock in the morning on Saturday. I think I saw a girl just walking around in her underwear. She must have been like a sexy something or whatever that, you can get away with on Halloween and not otherwise. So that was entertaining. But at the bowling alley, the kids were wrecked. Like they were just, it was not a good day for them. And my son's friend he bowls with just at one point came up to his dad and he's like, "Can we just go home? I'm just too tired to do this." It's like, you poor thing. So they exerted themselves, so thank goodness they get a day off of school today for election day. So
wow, things are canceled for election day.
Well, we vote at my son's school, so that's why they're out. And I think that happens at several schools in the area, so they cancel it.
Fair enough.
Yep. So I will go and do that afterwards. But for now, we have a quiz to talk about. Erica has a handout she's going to go through. I wanted to put this up just to let you know nobody got 100.
Yay!
Okay. I looked through the individual questions to try and get a sense of like where the errors were, and there's one or two that nobody got right. So if you went through this and you thought, this is hard, you're not wrong.
Yay.
I will say subjectively, my impression is that most of you captured the intent of the question, like which one should go down, you got right. It was unexpected consequences of reductions showing up elsewhere that was missed. So like, for instance, one of the principles here is that anytime you explain level 1 residual variance only, that results in less of a correction to the level 2 intercept variance that is true, and it will go up a little bit. So that seemed to be like where most of the errors were made, is just not anticipating the consequences of the changes in variance. But really the big thing I wanted you to get is to think about when I add a fixed effect to the model, what is it supposed to do? And that logic of what role does it play, what variance should it explain, is what I'm hoping to reinforce through this. So, Erica, you want to give it a shot? She's going to try. All right.
Excellent.
I will do my best not to jump in and interrupt you, but I can't promise it's not going to happen.
I appreciate it.
I'm just saying.
I have my cheat sheet, but
Yeah, I've got your sheet here, and then if you want me to do anything or write anything, just let me know.
yell if I
Yell.
say something wrong.
Yeah, correct you.
Yes.
I can do that.
Hard to ask, I know. It is this one. Yes. Okay.
Go for it.
Okay, so this was the equation that we started looking at that was given for the formative assessment. So first of all, which part of it was level 1 in the equation? Like what line? First line? Yeah. And then, so these two would both be level 2. Yeah. I didn't write that on here, and I referenced Lisa's from last time, and she did that of like level 1, level 2. But
Do you want to walk through the notation real quick just to make
Yeah.
sure we're all on the same page?
yeah, so yeah, this would be level 1. We have our outcome Y, PC for person and cluster. We have our beta 0 C. So this is our placeholder for the intercept. And the placeholder here is showing, here is the fixed intercept. And then we have the cluster mean for the first predictor. And I just put, no, you put -5. It's like, I put something later. Just to center that cluster mean. Then we have the U for the random intercept. Down here is the beta 1 C, the placeholder for the within cluster part of the first predictor. So we have gamma 1 0, and then U1 C for our random slope, and then of course we have our residual variance as the E. So I have P for person. Lisa does. I did the same thing because I copied you. Yeah.
So long as it's not IJ.
Yes. No IJK.
No IJK, ever.
Yes, P for person, C for cluster. Okay. So then In the first part, it was talking about adding the within cluster part of a cluster mean centered. I'm doing it because I keep thinking longitudinal too.
Yeah.
Cluster mean centered level 1 predictor is added. So in what line would we, of these ones, would we add it in? Number 1? Okay. And so what would the first letter be?
Do you want to add it? As we go?
Ooh.
Yes, I can. I'm not used to your keyboard.
Maybe this
I
keyboard
can
will
type for
work.
you.
I'm making fun of a different keyboard that lost the power of plus.
Oh yeah, I broke the power of plussing in Ariel's class, so. To zoom in,
Yeah,
Okay.
It was bizarre.
So what number would this beta be now?
2C. Sub 2C.
Okay. We have within cluster X2, it is PC.
Louder, because you're right.
Okay.
Okay.
And let me do this so we can see the new part easier.
Is she done, or is she missing something?
Should have something like a level 4 on line 4. Sorry. Maybe
Line 4, what should be here?
a gambling with 2 0.
Yep. So we have the placeholder in the first line, but we don't have
We don't have a random.
defining the placeholder. Is there a random effect here? No. Yeah, so this is going to be the fixed slope for the within cluster second predictor x2 that we have, but it's not random, so we don't have the u attached to that.
Okay.
So then what would happen to the residual variance now that we added these two parts? Down. Okay. And then the random intercept variance. We didn't do anything to say here. Yeah, this is what Lisa was talking about, of how this would then increase because we are decreasing the correction when we have the estimation of the true.
Yeah, so essentially, if you think about what true variance is, if you wanted to try and approximate that without a model, you would just calculate the mean across for all the clusters as an observed variable and get the variance of it, right, and those cluster mean differences. Well, that does not take into account the possibility that there's just chance differences across clusters, right? Like you would expect a little bit of variation just from normal wiggliness, and so that is quantified by residual variance divided by average level 1 sample size. So then what happens is you have the same intercept variance because it should not have been explained by a level 1 predictor, but then you're subtracting off less residual variance than before because you've explained some of it. And so then the result of what is considered true is actually higher than what it was in the previous model, at least to a little bit. You would not see it in very large clusters, like clusters that have a lot of people, but you will see it in small ones and in longitudinal data when there's fewer occasions than there tends to be people. So yes, random intercept variance does go up at least a little bit anytime you explain only level 1 residual. And by the way, I'm going to post this on the website after class, so you can have a full record of everything. Okay, cool. And you can take as much time to go through this as it takes.
Great. Okay.
Especially since Unit 5 is not ready for Thursday yet, so you would actually be doing me a solid if you went really slowly and thoroughly through this.
Okay, so random, slow.
Not like, well, we'll go with thorough rather than slow.
Yes. So what would happen to the random slope variance? And it's this one for the within cluster of the X1. Would that be affected at all?
Shouldn't be much.
No. So this would be same. So that one stays the same. So yes, a lot of you were good in terms of thinking of the within cluster is just solely the level 1, so that is going to just decrease the residual variance, and that is the one in its line, the E over here. But then yes, we have to account for the random intercept slightly increasing, and then random slope variance is not affected here. So then to the next one. So if we were then to add the cluster mean for the second predictor, what would we have to add? In what line should we start with? 2? Okay. And what should the number for what should the number for the gamma be? Yes, and then it will be cluster mean x2, and then c, and then we'll subtract it by something. And then are we done with this? Or do we need anything else? It's a cluster mean of x2.
Nothing else is needed.
Yeah.
Because it's already level 2, it's not a random slope, so
Yep, we have our gamma here going into the beta 0 placeholder, yeah. And then, so what would happen to the, let me,
Yeah, fix the highlighting, please.
yes. The joys of copy and paste. What would happen to the residual variance now? See?
And why is that the case?
Yeah, it's only level 2, so it's going to explain the one in its row. Well, I answered the next question.
Good job.
Well, they're tied together, right?
Yeah, so what happens to the random intercept variance? It goes down, yes. Mystery, really hard question. And then, is the random slope variance going to be affected? Nope. Yep.
And you'll note the answer choices were about the same.
Yeah.
Because things can wiggle a bit, and they will. But this is what should happen, like theoretically.
Of course, estimation doesn't want to be that easy to give us exactly the same.
Yeah.
Yes, okay. Oh,
Oh, wow, we got more questions.
no. There we go.
Ooh, special.
Okay. And then if we were to add then the interaction between the cluster mean of predictor 2 and the within cluster part of predictor 1, what would this interaction be called? Cross-level, yep. And what do cross-level interactions usually explain?
Yeah, level 2 variance,
Which type of level 2? Because we have 2 level 2s currently.
random slope.
Random, yes.
Where does it go in the equation?
What line should we start at?
So let's put it all the lines.
Every line.
Every line will
Nope,
just get.
one interaction only.
I will guess the second line
The second line.
would be from 0.
What part would we add? Because we have already the cluster mean and the cluster mean here. So these parts are already in for the placeholder for the,
You have your colon, or you'd be multiplying. But,
so this is the within cluster. This is the within cluster for the second predictor. and then we have our cluster means here. Would we do something?
Yeah, we wanted to interact with this one, right? So we gotta go here, gotta go here, gotta go in there.
Because this is where the fixed slope for that within cluster part is, and it has the hierarchy. If you were to put these two back in this equation, that's where, if you put the cluster mean here, it's going to interact with that within cluster part. So then we would add an extra gamma. And what number would this be? 2, 0. Yep. Oh, yep, nope.
One,
We already got one of those.
one.
There you go.
Increase first as you go down, increase second as you go across.
The first digit is tied to the
Grid.
beta is.
Yeah.
That's fine.
I don't have it lined up well right now, but yeah, the grid of how you look at it. This is x2.
Now technically, if you wanted to make it match, you could skip 1, 1 and save it for that one and do 1, 2. I think either of those would be okay. Because that way then it's the roll is the same across level 2 equations. But
Okay. And so then what would happen to the residual variance? So this part, since this is a placeholder, this, the gamma 1, 1 for the fixed slope for the cluster mean of the second predictor, it's going to go in here. So then we're going to have the fixed slope for just the within cluster part, and then this cluster mean is going to be timesing by that within cluster. So it's like separated out, but it's going to fall back in line with that.
yeah, like if you distribute this across beta 1, then it's this times this times this times this.
Residual variance should probably stay the same because we're working in level 2.
Mm-hmm. Yeah. And then the random intercept variance.
I got it wrong, but it should stay the same.
Yes.
Apparently.
Yes.
Well-
I'm going to agree with that, apparently.
So why is it apparently going to stay the same?
Now I'm assuming because it's on the line with beta 1, not with beta 0, it's not doing anything to the random intercept variance U0 and C.
Mm-hmm.
Yep, it already predicted that with the main effect.
Yep. And we have the random slope here, so that's what's going to predict in its line.
Did you answer the last one, or was that like this?
We did that one first.
Oh, we did.
Yeah, so the random slope variance,
Okay.
the one in its line.
The one in its row so far is the guiding principle. Until now.
Yes. Oh no.
Oh, you made it extra yellow.
Yellower.
I was trying to reduce the yellow. Okay. So then we're adding the interaction of the cluster mean of the second predictor and the within cluster part of the second predictor. So which predictor do we have a random slope for? The first one, yes. Because this beta 1c with the U1c for the random slope goes back to the within cluster part of the first predictor. So we're adding another cross-level interaction, but the level 1 part of the cross-level interaction doesn't have a random slope for it. So what would that be called? systematically varying. Yep. Because it's going to be differing based off of the cluster mean of the second predictor, but it's not going to be varying like for each cluster.
And where would it go?
Yes.
Why? Maybe.
Mm-hmm. Because this is
Yeah.
within cluster for x2.
Yeah. We're doing. Yeah.
You're outside.
You're out.
Yep.
Yeah.
Yep.
Out. Now you're in.
The joys of equation editor.
Mm-hmm.
And then what number gamma would this be? 2. And I'm just keeping it consistent with what we're
Sure.
centering the consonants, but it can be whatever. So then which variance component would this gamma 2, 1 explain? If we don't have a random slope for it.
I was thinking because you cannot have random speed for that to happen. That would be the plan that design for interaction. So I was thinking that you would go to 1 to 2, but that was so running my explanation of why that is. But I know that you will explain this with the random. And random should be the same.
Okay. So,
Can you repeat that?
yes, I was trying to remember how to phrase it. So, was saying that the residual variance should decrease, but not knowing why, and that the random slope variance should stay the same, and the random intercept variance should increase, but again, not knowing why. So if we look at the beta 1c again, and we like put it back into where the placeholder is, so if we put it over here with the fixed effect for the within cluster of the second predictor, it doesn't have, like we said, the random slope for it. So if we put it back here, what's in its line is now going to be the residual variance, since it doesn't have the random slope variance here to explain. So it's going to default back to the residual. And then this random slope is not for the predictor, or the cross-level interaction is not for the predictor that is in the random slope. So it can't explain that random slope because the level 1 part of it is the second predictor, and the random slope is for the first predictor. So that's why it's not going to explain the random slope variance. And then, as we talked about before, when the residual variance goes down, the random intercept can adjust a little bit and go up a little bit more. Does that make sense? Should I say it again in a different way? Or any
It's
questions?
kind of the same reason that was given on the first question, if I remember right.
Yes.
Okay.
I would also say, if you think about what E means conceptually, right? E is all the remaining differences of U relative to your group. So if you picture like a scatter plot of dots around like your line, well, maybe one of the reasons why you are off your line is that your cluster needs a different line. And so by giving your cluster a different line, theoretically the E's get smaller. So the cluster differences in the slope that we would have had here would have been taken out of E in the first place. Like it would be the E variance that gets partitioned. And so if you don't partition it into the random slope, it stays where it was in E. So that's another way I think to think about it.
Yeah, back to you.
But yeah, this is the situation where if there should actually be a random slope and you don't have it in there, then the cross-level interaction type 1 error rates are going to be sky high. So you have to make sure that the slope is there if it's needed. If it's needed is the tricky part, because if you have a small sample, you can have a likelihood ratio test that says it's not needed, but it might still be like strong enough to mess up things. So that's actually a study I did several years ago that got rejected, and I haven't had the courage to go back and fix it. It's just sitting in my file cabinet, you know. But
Yes, it reminds me of your like once upon a time there was an E, and that's how like we take out the different variances. So yeah, that's why the random slope is coming from that.
Yeah, that slide's in there somewhere.
Yeah, but I always like how you say it like.
Well, there was. Once upon a time, we had single level regression, and then we just started pulling variance components out of it.
It's that easy.
Yeah, it's fine. Are there questions so far, folks, or is this helping? Okay, big nods. Good.
Yeah, these are definitely, as we get lower, the trickier ones. So don't worry about saying the wrong answer.
Yeah, wrong answers only.
Yeah. So now instead of a cluster mean centered predictor, we're going to be adding a constant centered level 1 predictor. So if we're adding it just by itself, what would this be called? Smushed. Because we don't have the corresponding level 2 part of the predictor. So now this is going to be the same slope for both the within and between.
Where does it go?
On what line would we start with? Mm-hmm. And then we would have x3 minus something, constant centered. Oh. And it would be PC for each person in each cluster. And is that it? Or do I need to add something else? If we remember that the betas are usually a placeholder. Is that all I need to add? Or do I need to add anything else to the equation? As I said, if we remember that the betas are usually a placeholder.
You need that line for beta 3C.
Yep. And then what would the number for the corresponding gamma be?
Gamma,
Uh-huh.
3, 0.
Yep. And then do we need anything else, or is that it?
That's it, because we're not adding a random slope with the.
Yep. Yeah, and if we tried to add a random slope, it would be smushed, because it's smushed already. Yep. And then we get to the trickier part.
Yeah, the bold part is important.
Yes. So this predictor has a strongly negative within cluster slope and a similarly negative between cluster slope. So what would happen to the residual variance? And remember, this is a smushed slope.
Should still decrease because you're pulling, or you're hopefully pulling some variance out with the new predictor.
By pulling out, do you mean explaining?
Sure.
Yes.
I'm using your earlier, let's pull this lots of variance.
That was pull out for the random slope.
But still.
Yeah, that's different.
Yeah.
That pull out means partition. This pull out means make go away.
Okay, let's make it go away.
And then the random intercept variance. What does the smush slope say about what the between slope should be?
It says within and between is the same, right?
Mhm.
Yes, it's moved.
Yeah. So they're both constrained to be exactly the same. You're not giving it its separate slope. And so,
So it's pulling some variance, well, it's partitioning some variance away from the random, whatever. It's getting smaller.
It's explaining some of the
Yeah.
random and subvariance, so it should be decreasing.
Yeah.
So it would increase
Because
a
it's
little.
because it's smushed.
It would increase a little bit, but you're not gonna see it because it should go down. Because the between effect is in the same direction as the within effect, like you should at least get some reduction in your variance as a consequence of that.
Had we used the within cluster though, as opposed to the smush, then the random intercept variance should not change?
It should go up.
It should, just a little bit. Okay.
No, every time, except for the weird case, like when the residual variance is explained, the random intercept should increase a little bit. No, but this is because the between slope is the same as the within, and they're in the same direction. And then, I lost the mouse. Okay. What should happen to the random slope variance? Nothing, so it stays the same. Yeah, because nothing's happening to the random slope, it's just there. And then my favorite, the next one, which I did have to review what Lisa said about it last time when I took the class. Yes.
I have one question about the previous model. Because, Lisa, now that you mentioned that in this case both were negative, what happened if one is negative, the other is positive, and let's say we don't have a contextual effect because they cancel each other?
That's the last question. But thank you for foreshadowing that as well.
Yeah, but my question is maybe not related to that question specifically. It's about what's the relevance of the fact that both the slopes were negative related to random intercept variance and residual variance. Because to me, one thing is the conflated effect, regardless of the direction of the slopes, we know that residual variance and random intercept variance should decrease. So my question is, why is relevant in question 5 that both are negative? Because to me it would be the same case if both would be positive, or one is negative, the other is positive. Does it make sense what I'm saying?
Yes, so the negative doesn't matter, you're right. Like the story could be they were both similarly positive and the answers would be the same. Where I was trying to go with this is the situation in which there isn't much of a contextual effect and between and within are relatively similar. In that case, having one slope due to between and within is probably not that bad, and you would expect that slope to have explained residual variance because of the within part and random intercept variance because of the between part.
Mm-hmm.
But that only works to the extent that that one slope can do the job of two effectively. So then your other example, when they're in opposite directions, that's the last question because the story changes.
Okay, thank you.
And also because the smush slope is going to be more like the within slope.
Yes. Yeah, usually it's much more heavily weighted towards within.
You reminded me of that when I watched the video. To remember what you said about it, yes, because this one is a bit weird. So now if we have the strongly negative within cluster slope and then the strongly positive between cluster slopes, so again, they're going in different directions, but this is a smush slope. So the equation should be the same because we still have the same constant-centered level 1 predictor, but it's just the direction of the different within and between parts. So then what should happen to the residual variance? Decrease? Huh?
Yes, because the smush slope will be more like the within, so that residual variance should still go down.
And then what would happen to the random intercept variance? As I scroll down on my notes to double check. Increase?
So because they're in different directions, like within cluster slope, between cluster slope, are in different directions, but we're having it be smushed, trying to figure out, like, putting in the words, why would it increase?
Yeah, so if we have, like I said, the negative within cluster slope, so that is going down, it's going to be, the smush slope is going to be more like the within cluster slope, like what it actually is. So that is going to be explaining the residual variance part. But then, yeah, the between cluster slope isn't going to be correct. It's going to be saying it's negative when it's positive. So that misspecification is going to show with the random intercept increasing instead of decreasing. And then also when you have the residual variance decrease, the random intercept increases. So it's like both because the residual variance is decreasing and because the smush slope isn't correctly specified for the between part.
Yeah, if you think about the neutral case, if you have no between, like you assume the between effect is zero, then the random intercept variance shouldn't change. But we're actually assuming it's backwards from what it would want to be. You're making the model worse, so the variance will actually increase as a sign of misspecification. In chapter 9 of my book, in a longitudinal context, I report the results of a little simulation that demonstrates this. So you can actually see it happen, that the variances increase as a result of smushed effects in the opposite direction.
And then what should happen to the random slope variance? Is the no for nothing? Yeah. So it should stay the same because this is not a cross-level interaction.
Yeah, it has nothing to do with the first within the cluster predictor. That's the key. Only terms that have this variable as part of it could explain its random slope variance.
Any other questions?
Everybody gets 3 points. Ignore icon. I just wanted you to be able to see which questions you missed, but everybody gets 3 points for doing it, okay? That's all I'm going for.
Yep.
Cool. Nice job. Ta-da! I think that's worth a round of applause. Should we send a candy around again? Did you get any? Yeah, from Halloween. We're gonna have candy all of November. That's my plan, I think, or until it goes away. My entire cupboard is full of chocolate right now, and no good can come of that. Oh. Yes.
Can you repeat please what you said about the between cluster fixed effect for the random intercept variance? Why should the random intercept variance increase when the between and the within cancel each other? Would it cancel each other?
No, they wouldn't cancel each other because of the differential weighting of each. So what will happen in this case is that because the smushed effect is going to look close to the within effect, that's what it will be. Like it will show up as a negative slope, not as negative as it should be, but probably negative and mostly so. And so then what it's going to say is that the between cluster slope that should have been strongly positive is going to be entered as negative into the model. So it actually is going to make it worse than just assuming that it's zero.
Okay, got it.
Would it make a difference if the positive was a lot bigger than the negative and how that would work out?
Yeah, I'm sure you could come up with specific numbers that would, have different results. But just in principle, like if your variance goes up, that can be a sign of model misspecification because you're forcing something into it that it doesn't want.
Okay, fair enough.
That's the guiding principle. Okay, other questions? Yeah, that's a great one. How do I fix it? Delete. Well, I will tell you.
Put in the within and the between as opposed to the smush.
Yeah, what if I don't want to delete? Recenter? Well, so if I center, if we do that, what do I now have in my model as a fixed effect? Is it still smushed? What is it now? Just within. But I don't have between. So I'm not done yet.
Maybe between two, your level 2.
Which level 2? I've got 4 of them.
So beta sub-0 C.
Yeah, this one. This is where the main effects go of your level 2 predictors. This is where the interactions with x1 go. This is where the interactions with x2 go, and this would be where the interactions with x3 go. So since we're missing a main effect of this, we could add that, and let's call this x3. It's going to be 13, because why not? And what's this?
O3.
Yeah, O3, yep. So in this version of the model, we would have, I call this the within-between parameterization, because all the level 1 slopes become within, all the level 2 slopes come between. What if someone wants to set up the same model like that?
They're insane.
They're insane. Nope, they are what everyone else in the world does who's not me as a standard practice. Is this okay?
Yes, we need to compensate.
Well, this, just delete it. So this then changes the story to be a within contextual parameterization. So the level 1 slopes are still going to be within, even though they're tied to different variables, because they become within after controlling for the contribution of the cluster mean. These cluster mean effects are all going to be contextual rather than between, and the difference is whether or not you're controlling for the effect of the corresponding level 1 predictor in estimating the level 2 slope. If you are controlling for it like this, it's within contextual. If you're not, it's within between. The difference is whether these variables at level 1 contain absolute information, like in currently, or only relative information to the cluster. If they contain absolute, then the contextual effect is what you get at level 2. So for the most part, with respect to fixed effects, you can do either. So long as, if you do it this way, so long as whatever you have at level 1, you've done a comparable version at level 2, you're good. So we're missing some stuff. Are the main effects okay? So main effects at level 2 would be right here. Main effects of each of the level 1 predictors are the terms that start out these level 2 equations. Are they okay? Okay, what's wrong with them? These cross-level interactions would be smushed because we don't have the corresponding interaction at level 2. What about this random slope right here? It's smushed too, for the same reasons. So just, if you switch it back this way, you got to be extra careful that everything has been unsmushed, if possible. There is no way to unsmush this random slope, like practically speaking. So this is where you would have to change your model back to be the within cluster version, at least for the random slope. Okay, other questions or things you want to talk about with respect to this? Yes?
So using the in-cluster and contextual fixed effects in this model doesn't mean that to unsmoosh your cross-level interactions, you have 2 cross-level interactions, but to unsmoosh both, you would only need 1 quadratic effect?
Nope, you need 2.
But in both cases, we would need the cluster mean of x2, right?
So this one is with x1, so you would need it with the cluster mean of x1 instead. So it's the level 2 version of the level 1 predictor that we're worried about. So to unsmush this cross-level interaction, I would have to add a level 2 interaction with that one. And Yep, and the same would be true for this term or this term right here.
Okay.
Okay. Thank you. So I will post this so that you have a record of everything. All right. Should we look at example 4? Try to wrap it up, maybe? We'll see. It was a valiant effort, Erica, to stretch it into a Thursday. I appreciate it. We still have actually a few, several things that we can talk about. So it may be that we have some of this next time and then we do the new thing next time. We'll see. Where we left off on this, I think, random slopes, we got 2. We started with cross-level interactions, I think. Trying to remember. It's been a while. I think we got to random slopes and cross-level interactions. I'm almost positive we did. Which random slope is it for, though, is the question. This one. Okay, yep, I remember this. This is where we were. So in the story so far, in a Midwestern rectangular state, 10th grade math is related to free and reduced lunch status in its students. At level 1, if you are a student who gets a lunch discount, your math is predicted to be 8.5 points lower than a student in the same school who does not get a discount. So clearly we should stop feeding kids lunch because it's lowering their math scores. Just make them pay and it'll be fine. How's that for a causal attribution? We added a random slope around this fixed effect, though, allowing clusters to have their own version of it. And that random slope contributed significantly to the model. There's my likelihood ratio test for that. And we did a confidence interval to describe the expected slope variation across the clusters in the sample. And the interval is minus almost 16 to minus 1. So on average, it's an 8-point gap, but the size of that gap varies quite significantly across schools. So then the question was, why? Perhaps it depends on how many poor kids are at your school. There may be less of a gap in schools that are more advantaged or less advantaged. I'm not sure which way it would go, but I'm pretty sure that that would matter. So I added in a cross-level interaction with the cluster mean. So this was the question, does it suck more to be poor in a school with more poor kids? That's the key idea. So we tried to interpret some of this stuff, and I think we got to the next model, and that was it. Does that sound familiar? Okay. So this model, is this going to be, let me go up here, for the fixed effects, I think this is good enough to look at. For the fixed effects, is this going to be a within contextual version of a model or within between? In the way that I've set it up with respect to the fixed effects, within contextual or within between? Within contextual, why would you say that? Because you're right. Yes, this is the original binary version of this variable, not the within cluster centered version. Therefore, the level 2 effect is going to be contextual. So the intercept then is conditional for a student who pays for lunch as a 0 at level 1, and in a school where 30% of the students get a discount as level 2. That student is predicted to get a 50. If a student gets a discount, their score is predicted to be lower by 8.5 points or so within that same school relative to students who pay for their lunch. After controlling for whether or not you pay for lunch, for every additional 10% more poor kids in your school, the whole school's math score is lower by 1.9. So for every 10%, you can move the decimal over one place to talk about that, and it'll be a little bit more understandable. So this is a contextual effect. This means that even if you're not economically disadvantaged, the more children like that in your school, the lower your school's average performance. this is a cross-level interaction between the two halves. What we would want it to mean is how the effect of student lunch is moderated by school composition. But before I would dive in and talk about that, is this okay? Or is this broken? Yes, these effects are negative, and the interaction is positive, which would mean that the effect is weakened in schools with more discounted students. However, this effect would be smushed if we didn't have this one, right?
You have to unsmush your
So this effect would be smushed if we didn't have, yeah, the interaction is smushed. What this is saying in an interaction is that you're saying the extent of moderation by the level 2 predictor is the same at the within level as the between level. That's what it would mean. So we can fix it by adding the corresponding interaction at level 2, which is where we get into the weird looking quadratic effect, because it's the moderator times the predictor that carries the between effect, or the contextual effect in this case. So that's where we left off, I think, is this crazy model. So putting it together, now this is how school composition moderates the within effect. And they do work in opposite directions. It sucks less to be poor if you're in a school with a lot of poor kids. However, if you're in a school with a lot of poor kids, your scores are lower. So that still sucks. Poverty sucks broadly construed. So the pattern of this slope that's being created is a negative slope that's speeding up as you move up the variable. So you get a stronger effect on math scores the higher you go into school composition. Nonlinear. And this is the point at which your reader will beg for a picture, and you will need to give them one. So given that the model is phrased as within contextual, I made some pictures that show on the x-axis just the zeros and ones for lunch status, and then different lines for different school compositions. So should we take a look at those? Would that be useful? Okay, let me get the Excel sheet that made them out. In your example 4 syntax, by the way, I've included prediction commands in both Stata and R that generate predicted values, so you don't have to do that manually in Excel, but then you can make the plots in using whichever software you want to. But I think it's useful sometimes to see things like the formulas, just for... I learned the word pedagogical is incorrect, by the way. Did you know this? It's andodogical or something for grown-ups, andogical. Because ped means kids. And while I think of you as my kids, you are decidedly grown-ups.
I also think there's a lot of overlap in how you learn that if you're an adult or
There may be, but I am very aware that my job is significantly easier than my son's teacher's job, for example, right? That's pedagogy. You got to keep the kids from killing each other and like keep their attention, you know.
police work.
Yes. Plots, that's where I wanted to go. Okay. So my approach to this was brute force because I thought it would be useful and also because I didn't trust myself to program something before I could figure out what I was doing. So in this spreadsheet, this is from the example 4 download, I entered in all the fixed effects for this model. And in gray are things that are not being used. So here are, for example, I have 4 different kinds of schools that I'm going to create. Let's see here. Oh, no, never mind. Yep, I got it. And I'm looking at my own work, trying to put it back together. So I put in 0, 1, 1 because I'm creating 3 different kinds of kits in this example, because eventually we're going to split out the freeze and reduced in the final model. I then had to figure out what to do with level 2. And so then one plot, I held school composition constant with respect to holding the proportion free lunch constant, holding the proportion reduced constant, and holding the proportion paid constant. So we don't yet have the difference between free and reduced in the model, but I still thought it would be helpful just to look at the plot here. So what I have then on the x-axis is the level 1 predictor in its original form, and on different lines are different combinations of schools here. And so the distance between the lines is the contextual effect. The fact that these gaps are not the same size as these gaps, the gaps narrow, that's the cross-level interaction. So there's a bigger difference of school composition among the paid students. The effect of student poverty is smaller in schools that have more poor kids. That's the negative effect, and then the positive cross-level interaction working against it. It's hard to tell, but if you zoom in very, very far, do you see how purple and blue are farther apart than blue and green and red? Just that's the quadratic effect. So there's a bigger difference as you move up the variable in terms of school composition. So these are each 10% apart, and there's a bigger gap per unit change as you move up. That's what this is showing. So pictures like this, I think, are really, really helpful to explain within effects and contextual effects, because usually then you can think about like what happens to the people in the study, and then what does that look like for different kinds of groups as your moderator. We haven't got the second half of the story yet. So in terms of interpreting these things, I think we did that. So these two are responsible for the parallel lines, non-parallel lines converging. The interaction term reduces the size of the gap as this moderator variable goes up. All right, I think that's all of that. I added a little function that converts these individual slopes to effect sizes. So you can report those as Cohen's d units of standardized mean differences. So like that might be useful. How different are the kids in this reference school? A Cohen's d of 3, that's kind of big, 3 standard deviations apart. Partial R's are also in a correlation metric, so for continuous predictors that might be more understandable. You can supplement individual slopes with pseudo R squares and total R squares, so we've got those down here. I also asked for the corresponding between effects, and so then you can get those estimates and effect sizes out of this function. And then we have what should have happened in terms of adding new effects. So which variance component should have been explained by this new quadratic interaction at level 2? What did you say? Random intercept. Let's go up to the equation. The new yellow term is right here. There's random intercept right in its line. Ding, ding, ding. That's what should have happened. That's what should have happened. Exactly. Let's see how neatly that happened. We have adding the level 2 interaction. Didn't explain much intercept variance, just a tiny bit. Did explain slope variance though, by unsmushing it. I think that's the reason for this, is because what was there before was not the cross-level interaction that wanted to be there, because it was the smushed version. So we've actually explained more slope variance by correcting it. So there's an addendum to when things can become in unexpected ways. Okay. So do you think there's a difference between reduced and free? Because that's what we haven't looked at yet. So I added in the contribution of that second variable. So just to remind you how these variables are coded in this example. The first one is coded like this. So up to this point in the example, we've been lumping together reduced and free as one group. The second variable that I'm now introducing as a predictor splits out free from reduced. So now the interpretation of this coefficient, this variable, is not going to be discount, but it's going to be specifically the difference between paid and reduced. And then this one will pick up and give us specifically the difference between reduced and free under this coding scheme. Now scroll. I'm at 3, I know that. I'm at 4, yeah, I'm at 4. I know I made it past 3. There we go, layer 4. There we go. So I am adding 2 things at once. We're picking up a level 1 predictor for paid and reduce versus free, 0, 0, 1. That level 1 predictor has a beta 3 placeholder that now has a fixed effect in level 2, only fixed effect so far. And in the level 2 equation for the intercept, I have added a main effect of the corresponding cluster mean. That tells us the proportion of students who get free lunch, which is 0.19 on average, which is why I picked that value as a centering point. So adding those things in, here's what we had before, here's what we have now. So which of these fixed effects have changed their interpretation, do you think? The intercept?
That one did not.
Yeah, have we changed who the intercept is for? We haven't. So the intercept estimate might change because the prediction has changed, but who it's for has not. What about this one? It was -8 before.
Should have changed because that's on the level 1 and we added a level 1 so they could balance themselves as needed.
Yep, this one changes because it used to be paid versus the combination of free and reduced as one group. Now, given the addition of splitting out reduced and free, the first contrast is just paid versus reduced. The second one is reduced versus free. So it looks like there is a difference at the student level with respect to whether the kind of discount you get, let's say that. How about these ones? This one has changed in a similar fashion because I've included that cluster mean. So this one is tracking the effect of proportion of students with reduced lunch now, and this is tracking the effect of proportion of students with free lunch. So this is still a huge contextual effect. This one, not so much. So it looks like there's not much of a difference between reduced and free at the school level, but there is more of so at the student level. If I want the between slope that is implied by these two, then I can get that. So the level 1 effect is negative, the contextual effect is positive. If I add those two together, I end up with a between slope of 2. Non-significant, actually. Yeah. Mm-hmm. So whether they need to be separated is an empirical question, I think. The benefit of the coding scheme that I'm using, so let me see I'm on page 15, okay. I can scroll faster next time. A traditional coding scheme would not look like this. A traditional coding scheme would pick one group as the reference and create contrasts that compare each other group to that one. So that coding scheme would look like that instead. That's a traditional one. The disadvantage of a coding scheme like this is that even if these two groups don't need to be split, reduced and free, you still need both these contrasts in the model because you have to differentiate each from none. The advantage of doing it this way is that should you learn that this doesn't matter, you don't have to have it in the model anymore. Then this goes back to lumping the two groups together, which would be empirically supported at that point. So this is just a choice in terms of how you set these things up. Either one will lead to an equivalent model in the sense that you're still splitting apart three groups somehow. Did that answer the question? Yeah, so like this kind of coding scheme is useful when I think you have like one group that is definitely a comparison, and then there's a set of other groups that are like qualitatively different. So if you wanted to examine like what is it like to be a member of a racial minority or something, right? You might have minority and non-minority as like higher order categories, but then there's lots of different ways to be in the minority. So then it's like if you have the minority non-minority distinction first, then you can see how many of the further sub-distinctions are needed amongst the different flavors within that one heterogeneous group. But if you don't have that kind of hierarchical organization, then just a standard coding scheme where you're comparing each group to a reference would be fine. This is also useful in ordinal settings, I think, broadly construed, this type of coding. So. Question?
Yeah, Lisa, in the case of the cluster mean, the new cluster mean.
The new cluster mean.
Yes, for free.
Mm-hmm.
What's the reference for that slope at level 2? Is that fixed effect capturing the difference between a theoretical school entirely composed of students who paid versus those who didn't pay, or is comparing something like the incremental thing based on the coding scheme we are using here?
It would be capturing it's incremental because it's contextual, if that's what you mean, like above and beyond student status. This would be capturing for a change of 0 to 100% in paid versus reduced. Because like even though the variable itself has free in it, once you control for this other one, then it becomes just reduced. Yep.
Is the same at level 1?
Yes. Yes,
Okay.
it's the same at level 1 as well.
But before we said that when we use this incremental coding scheme, we are saying how much this third group has with respect to the second one. Is that correct? Or because what you said to me sounds like the traditional dummy coding scheme?
I very well may have misspoken. Let me try that again then. Yes. As it turns out, I am imperfect. I hate to break it to you, but it happens occasionally that I say the wrong thing, especially in front of people on a recording. Yes, this one is paid versus reduced. This one is supposed to be reduced versus free.
Yes.
And the same is true at the contextual level as well.
Got it. Okay. So that 6.4 for our second cluster mean, that would be capturing the difference between, let's say, a theoretical school entirely composed of the students with reduced price lunch?
I think so. I think of that, because it starts to get weird to think about
I
these.
think so. Okay.
Yeah, and that's why I made 3 different plots to try to pull this apart in terms of where is the difference.
Got it. Okay.
And also, I mean, just thinking about schools, if you have a lot of free, that means you also are probably getting more resources from government to help, which could increase your scores, which is what you're seeing.
Yeah, I don't know. This is not my area of expertise, but there's lots of reasons.
That was my classroom. I had a classroom like that. It drove me nuts.
Yes. So 141. We're not going to get through this today. So we'll finish it on Thursday. I'll let you know if we have stuff to talk about on Thursday with respect to the next unit. I want to make sure that this is all really solid, though, because like the next unit is more optional. So if it feels like we need to do more review or more discussion, we can do that. But not today, because we're full, right? Heads are full, and it's time to go almost. All right, anything else I can help you with at the moment? All right, then I'll hang out since I have to be here for my next class anyway, if anyone wants to chat about their projects or otherwise. Thanks for being here.
Homework 3 is next Monday. Yes.
Yes, homework 3 is the next thing. It's been out for a while and it's due Monday.
Just making sure of it.
I think I opened a spot for the project check-in, didn't I? If there's not one, I'll make one.
I think so.
Okay. Do you need to, that's not due until the next week. No, it is not optional to check in with me. No, because this is to ensure that you're not starting your project the day before it's due. Okay, that's what this is for. Because I'm saving you from yourself otherwise.